Good morning. Today we'll be looking at chapter 15. We're going to be looking at wave motion. Now, waves, when people hear about waves, this is one of those common terms that gets used when people are thinking about physics, and we're going to find that there's a number of misconceptions about what a wave is and how the motion works. So I'm going to warn you, don't think, oh, waves. I know what waves are. I've talked about waves in all my school classes, my whole educational career. But let's take a look, careful look, at what we are referring to when we talk about waves. So let's start with, here is a string of some sort, or rope. And what we're doing is, on this cord, we're creating just a single pulse. So we're creating, what I'm going to say is a disturbance. So my highlighted comment here is, a wave is a disturbance that propagates through a medium. So this is creating a disturbance. The medium, in this case, would be the string that we've got here. And so the disturbance is just a single pulse. The person lifts the string and then brings it back to equilibrium position. Now what happens is this, in the original picture, we've got an equilibrium position for each one of the points on that string. By creating a disturbance, what we find is that one part of the string is connected to the other part of the string. All the individual pieces of the string are connected to each other. So creating a disturbance at this region does not stay isolated at that location. Instead, the disturbance propagates. So by creating a disturbance at one region, that disturbance propagates along the length of the string. Now, what happens is, as this disturbance propagates through the medium, there is a particular pattern that each part of the medium experiences. So right here, we can see, here's part of the medium returning back to equilibrium. But because of the disturbance that was generated and the way it's propagating, this part is lifting away from equilibrium. So what's interesting is when we create these disturbances and they propagate through a medium, to some extent, they propagate with kind of a constant profile. If there's no damping, if there's no energy damping along the way, then ideally the string will maintain this same profile, and that profile will propagate. Now, there's two different types of motion going on here. We can say, well, there's the wave motion, and the wave motion refers to the speed at which this disturbance is propagating and to the pattern as it shifts from one region to the next. But then we can ask, well, but what's the medium doing? What's the material that actually supports this wave propagation? Well, individual pieces of the string are actually just going up and then coming back down. They go up, they come back down. In this case, it's a single pulse, and that means that the medium just moves away from equilibrium once and then returns back to equilibrium. That process happens sequentially along the length of the medium. Now, this is just one pulse, but we could have many. We could have what's referred to as a periodic wave. A periodic wave would be a series of disturbances that are set up within the medium. And if it's a series of disturbances, then we're going to have a series of these pulses that propagate along the medium. All right, so I'm going to come back to this statement a lot. It's a disturbance that is propagating through a medium. That's our definition for a wave. Now, a lot of times in waves, people go, well, waves are like this, right? So waves have to always be doing this, and we're going to find out that's not necessarily the case. Even the single pulse here doesn't necessarily follow that description. So one of the characteristics of wave motion. Now, this would be a series of pulses that are propagating through this medium. So this would be something where we've got something set up to create a series of pulses. And in this case, the shape of the pulse looks kind of like a sine or a cosine function. Now that doesn't have to be the case either, but we are going to be using sines and cosines once again in this chapter, same as what we did last chapter, looking at oscillatory motion. Because we find that for waves propagating through a material, the motion of the medium back and forth can often be represented or approximated as simple harmonic motion. So what that would say is, oh, if I got a whole series of waves going by, then individual pieces of the medium are oscillating back and forth, and that creates the wave effect. So again, there's a wave speed, a rate at which these pulses are propagating through the medium, but there's also the motion of the medium itself. And the individual parts of this particular medium have a displacement and a velocity and an acceleration that probably matches up with what we saw in chapter 14. We can treat this as some kind of a harmonic oscillation that individual parts of the medium are undergoing. So let's take a look. Amplitude, we should be familiar with that. Amplitude is the maximum distance that the medium shifts as it oscillates back and forth. The wavelength is the distance from one pulse to the next. Now there's a relational formula that says that the wave speed, the wavelength, and the frequency of oscillations are related by v is equal to lambda times f. Now remember, this is not a formula of causality. This wavelength and frequency in the formula are not telling us why the speed of propagation is what it is. The speed of propagation, we'll find, is due to the properties of the medium. So whatever, depending on how rigid the medium is, depending on how large the mass is, what the density of the medium is, those properties are going to determine how fast disturbances propagate. All right, so amplitude, wavelength. Now, period and frequency. I'm going to actually start with period. So when I look at the individual pieces of the medium oscillating back and forth, well, there's a period of oscillation and a frequency of oscillation, and we saw that in chapter 14. So good, so again, chapter 14 is a good reference to work from when we're looking at a lot of stuff in chapter 15. So if I look at individual pieces of the medium as they oscillate back and forth, those individual pieces will have a period and they'll have a frequency. Now what happens during one period of oscillation, let's say that this part of the medium right now is at this location, and what it's going to do is it's going to start oscillating back towards equilibrium. What that represents are these locations of the disturbance. This profile is going to be propagating, let's say it's moving to the right. It could be moving to the left, but let's say it's moving to the right. And so as this wave propagates, what that means is that this part of the medium can look to where the wave is coming from, and it can see its future. So if I am this part of the medium, I'm looking at the wave coming towards me, and what I can see is, oh, pretty soon I'll be here, and then I'll be, in terms of my height, I'm going to stay right here, but as the wave propagates, I'm going to drop to this height, and then I'm going to drop to here, and I'm going to drop to here, and drop to here. By the time I drop to here, that means this part of the wave has reached that location. And then as the wave continues to propagate through, this part of the medium will oscillate all the way down and then come back up. Now, by the time it has oscillated through one complete cycle, one period, that means that the profile, the next crest, has reached this location. So this one cycle within the wave, as it passes by this one point, is telling us that this part of the medium will oscillate down and back up. It will complete one cycle. So that says that during one period, the wave profile moves one wavelength of propagation during it, and that says that the speed then of that effect is going to be related to wavelength over period or wavelength times frequency. So that's how those are all related. Now, with the wave, sometimes we talk about crests or troughs. That's really kind of your own particular point of view, right? Why is that a trough and why is this a crest? Maybe this is a crest and that's a crest. Maybe all the peaks are all crests. And then we can measure amplitude from the equilibrium position out to one of the crests. Okay, slinkies are great to demonstrate wave motion. We can take a slinky, grab hold of it, start creating these disturbances, and what we'll see is a series of pulses traveling away from the location where the disturbance was created. So in this case, we can see that there's a wavelength here. Now, I can shorten that wavelength by oscillating the slinky faster. So if I create these pulses at a higher frequency, then the wavelength shortens. Now, the speed at which the wave propagates, the disturbance propagates, will depend on the tension within the slinky and how heavy it is. Specifically what the density is, how much mass per length the slinky has. Now, if the motion of the medium is sideways, what we have indicated here, the medium's going back and forth like this, while the wave direction is in this case, we're designating that to the right. If this is perpendicular to the wave direction, we call this a transverse wave. So there's a transverse disturbance that propagates through the medium. We can also demonstrate with a slinky what longitudinal waves look like. Longitudinal waves would be a disturbance created by creating a disturbance in parallel with the length of the medium. So if this is the length of my medium, I can create a disturbance this direction. What that will lead to is compressions and expansions. So there will be, and the compressions will propagate through the medium. So we'll end up with these compressions that are propagating through the medium. So there are regions where there are compressions, regions where there are expansions, and that effect makes its way through the medium. So in this case, there's nothing oscillating back and forth. There's nothing waving like this. What there is are individual pieces of the medium moving back and forth in a longitudinal or parallel direction. I always think of this in terms of, transverse means perpendicular, longitudinal means parallel. And you go, why didn't they just call them perpendicular and parallel? But they don't. So we have to be ready, you guys have to be ready to think in terms of the new vocabulary. Transverse is perpendicular wave motion. Longitudinal is parallel wave motion. Okay, so disturbances can propagate in these two different manners through a medium. Now, we should say this too. If it's a solid material, solid materials will sustain a transverse or a longitudinal disturbance, a transverse or longitudinal wave. Liquids and gases only support the longitudinal ones. In a solid, there are restoring forces that will bring the a restoring force that will bring the medium back to equilibrium from a transverse direction. But that's not true in a fluid or a gas. So in a fluid or a gas, we can set up these compression waves, and the compression waves will propagate through that fluid. All right, here's a good example with that. Here is a drum. Somebody's playing the drum here, and the drum head is oscillating back and forth. So if I'm hitting a drum, I'm setting the surface into oscillation, into vibration. And so what happens is the drum head comes out and compresses a region of air, and then it oscillates back and creates what they're calling an expansion, or what's also referred to as a rarefaction. Now, rarefaction is kind of a, where else do you get to use the word rarefaction other than in talking about these low density regions within a fluid that are generated by these disturbances. Now, this is kind of exaggerated. They're trying to really emphasize these compression regions. It turns out that the amplitudes of oscillation with these waves and with sound, basically what we're talking about here is sound. The amplitudes that we create, or the pressure variations, are actually quite tiny. So you don't necessarily create really large variations in compression or in rarefaction. They're pretty subtle, but we are able to hear those, and they definitely have an effect. So anyway, that's a good picture to come back to too, to think in terms of a longitudinal wave propagation. And these compressed regions occur when two different regions of the air, the medium, whatever, come together, and then they oscillate away from each other, and that creates the rarefaction. So again, it's a synchronization of sorts as this effect propagates through the medium. So let's take a look at some of the wave speeds. We talked about this a bit before. If I have a string or a wire that's under a certain tension, what we find is that the speed of propagation of the wave depends on the tension, and it depends on how heavy the string is. Specifically, something we call mu, which is linear mass density. It's the mass per length. Sometimes we write this as dm dx. How much mass is there per length in this particular wire or this particular string? The heavier something is, the more mass per length. That slows down the process. This is, once again, the inertia effect that we're seeing here with increased mass. The tension for a wire, something like this, heightens the connection between individual parts of the medium. So if I take a string, say a guitar string or something, and I put greater tension in that, the different parts along that medium, the string, are in more immediate communication with each other, and the wave propagates faster. Let's see. It says here, as expected. So I guess maybe that's intuitive, that the velocity goes up if the tension increases. Anyway, if you're tightening a guitar string or a piano string or something, you're doing that with the intent of increasing the wave speed. And if you go back to that previous slide, you'll see if you increase the wave speed, you very likely will increase the frequency at which that string is vibrating. Let's see. This is a force diagram to try and, to me it's a force diagram of kind of plausibility, indicating why this would happen, but we're not so concerned about that. These are a little complicated. Going back and looking at these force diagrams and trying to figure out why these speeds work the way they do. So let's take a look at an example. Let's say that we have a wire, it's a copper wire, it's 80 meters long, so it's not short. This goes most of the way across the soccer field or football field at 80 meters. The piece of copper is 2.1 millimeters in diameter. Now, I didn't know copper was that sturdy, but maybe you can, you certainly do. Anyway, a lot of wiring is done with copper. 2.1 millimeter diameter copper wire stretched between two poles. A bird lands at the center point of the wire. So they are treating this almost like an electrical wire between a couple of poles. When the bird lands, it sends the bird lands right in the center, and sends a wave pulse in both directions. Now the wave pulses can reflect. So this is just kind of a single pulse, or a few pulses. So let's say the bird lands, the pulse goes out, reflects off these points where the wire is held in place. And that's one of the interesting features with waves, is that if you've got a firm connection at one end, you can get reflection of the wave from that location. So this pulse goes out at some speed, it reflects, it comes back at some speed. The wave speed, we said, was given by tension over mu, where mu is equal to the mass per length. Now the mass per length is a little tricky here because all we have to go with is that it's made out of copper and that it has a certain diameter. So how much length would that be? And what we can do is we can say, well, here's the copper wire. Here is its total mass. Here is its length. Here is its radius. Now, the length was given as 80 meters. The radius was given as 1.05 millimeters. So they gave us a diameter I divided by 2. The mass of that wire is going to be the density of copper times the volume of the wire. And the volume of a wire, it's got a circular cross-section, it's a cylinder, isn't it? So it's going to be pi r squared, cross-sectional area, times the length. So what we're after is mu. Now what I can see in this formula is if I divide both sides by L, then what I've done is calculated mu. Mu is equal to m over L. And that gives us the density of copper times the cross-sectional area. And copper has a density, I looked up, at 8,940 kilograms per cubic meter. So make sure that you're in kilograms per cubic meter, because we're going to need standard units in here. So the tension is going to be in newtons. I need that mu to be in kilograms per meter. So this is currently kilograms per cubic meter. I have to multiply by the area. And, oh, here it is. So the mu, there's the density, and here's the area. So I didn't calculate that individually, but I calculated it as pi r squared. So putting all that together, I am getting a mu value on this that says it's 3 grams per meter. So this much of the copper wire is only a couple millimeters in diameter, is apparently 31 grams. So it's 31 grams. Yeah, that sounds reasonable, right? So 31 grams per meter seems about right. Now what that says the tension will be then, the tension will be given by mu v wave squared. So from that formula. So I'm using this formula, solving for t, and then plugging in the numbers. Here is the mu. There is the speed of the wave. And the way we got the speed of the wave is this. It said that the pulse went out, reflected, and came back to that very same location. And that took 0.75 seconds. So that's pretty fast. It went 40 meters out, 40 meters back. And so that's a total of 80 meters that the pulse traveled, divided by 0.75. That gives us 107 meters per second. So putting that into my speed of the wave, it says that the tension in that copper wire is 343 newtons. All right. So by observing the speed of propagation of the wave in the copper, we are able to go back and figure out what the tension must be in that copper wire, knowing what its diameter is and knowing that the copper wire was made out of copper. All right, here's a couple of other velocity formulas. So if I have a solid material, I can take the elastic modulus. Think chapter 12, right? So we learned about elastic properties there. Here is the elastic modulus. I can divide that just through the density and take a square root. That will tell me the speed at which waves are propagating through a solid. And then for a fluid, for water, for example, or for air, we can use the bulk modulus divided by the density, take a square root, in order to calculate the propagation speed of the longitudinal waves that would propagate through a fluid. So I can use bulk modulus, elastic modulus, we can use the tension for a one-dimensional string or wire, all those speeds. Okay, let's try a couple wave speeds here. So let's think about air. Now in air has an adiabatic bulk modulus that is given as 141,800 newtons per square meter. So that's how much air resists being compressed. And the density of air at 20 Celsius is 1.20 kilograms per cubic meter. So using the formula that they provided, the bulk modulus divided by the density, that's giving me 343, and that's what we observe. We observe that the speed of sound at about 20 Celsius, 1 atmosphere of pressure, is 343 meters per second. Now if the temperature of the air goes down, the density actually goes up, right? As the temperature goes down, the air molecules settle down a bit, the air gets heavier, there's more air molecules. The atmosphere actually drops a bit if it's colder. That part of the air will compress. And so that's more mass, that'll slow the process down. Okay, so the speed of sound goes down as the temperature goes down. Let's see, this, so this is the speed of sound in air. And in water, the bulk modulus 2.1 10 to the 9th, so see how different the bulk modulus is. And that's just saying the air is very easily compressed, the water not so much. And that means that the water molecules are in more immediate communication with each other than air molecules are, right? If something happens to your neighboring water molecule, the neighboring water molecules know right away. You'll know, as a water molecule, you'll know right away if your neighboring water molecules go into oscillations. The air molecules not as quickly. Now the density of water is much higher. So the bulk modulus is larger by, what is that, 10,000, right? So it's 10,000 times the bulk modulus. And then the density is about 1,000 times higher, so you have to take both of those effects into account and then do a square root. It turns out that in water, sound is traveling. These disturbances, I mean, this is sound, right? 4 or 5 times faster, something like that, 4 or 5 times faster in water than it is in air. All right, here is an echolocation example. It says animals can send out sound and learn about their environment. Here we've got a whale that is sending out a frequency. That's a really high frequency, 100,000 hertz. So a kind of an ultrasonic disturbance through the water, and then listen for the return, listen for the echo. Now, what we're saying here is the time that it takes for the sound to come back. It's got to go out 100 meters, and then it has to come back 100 meters. There's an obstacle, and it's 100 meters away, and we want to find out how much time it's going to take for that sound to return to the animal. And so this is 2L divided by V is going to be the amount of time. Now the speed here is the bulk modulus over the density. This time I'm using a little bit different density. I'm using the density of ocean water that has all those sodium and chlorine ions included. So it's denser. And then the speed then that we're getting here this time is, and then I looked up the bulk modulus for ocean water, and it turns out the bulk modulus is larger. So the bulk modulus is larger. The density is larger. Anyway, ended up with 1511 meters per second. So I've got this formula that relates wavelengths, frequencies, and wave speeds. And so the first thing they wanted us to do was decide what's the wavelength. Now, the speed we got is 1,511 meters per second. So these disturbances are going out really fast, one after the other. And the frequency, though, is 100,000. So 100,000 per second are being generated, and they're propagating away really fast. The distance between one disturbance and the next works out to be 1.5 centimeters. So that's kind of fun to think about, right? I'm sending out a series of disturbances, and so it's a series of compressions. These are compression waves in the water, in the ocean water, and they're spaced 1.5 centimeters away from each other, and there's hundreds of thousands of them, and that's the spacing between them. And then the time then that it would take to return, the distance here, how much time does it take to go one way? I'm thinking I only solved for one way, maybe I need to solve. Oh, no, I didn't. I need to double that number. Sorry about that. So that number needs to get doubled. I only allowed, I certainly wrote this down fine. This one was 2 times 100, but I did get the 200 copied over here. So this is only one way. So one way is going to take 66 milliseconds. It's going to take 66 milliseconds to come back. Sounds like 132 milliseconds that it's going to take. Okay. So it's just a matter of milliseconds to pick up the reflected signal. Now what's kind of interesting is you go, well, wait a minute, I've got signals going out, and then I have reflected signals coming back. And what that creates is an effect we'll talk about more, is superposition. You can actually have more than one wave, more than one disturbance propagating through a region, and they can be propagating in different directions. And the waves, these disturbances, at least in kind of the idealized model, to a fairly good approximation, can just be treated as if they pass right through each other. And so you can still get the information even with multiple disturbances propagating through the same region. All right, here's a picture of water waves, and what we have to do with water waves is say, they're not a good example. So when we're talking about waves, don't start with water waves, even though I have to say that's a really pretty picture. So this is a really pretty picture of water waves being set up, and here is this disturbance that's been generated. So something got thrown in, and it set that region of the water into motion for some period of time. It doesn't go on forever. There's a damping effect that takes place. And so that center region oscillates back and forth and then damps out, and that energy is propagating away from that region, and you can see the waves. Now, these surface waves are actually more complicated than what we've talked about. I mean, they certainly look transverse, right? They look like they're rising and falling, but that only is occurring because we're at the surface of the water and gravity is providing a restoring force. So if you look at the actual motion of the water as these waves go by, it's more complicated. So again, that was a really pretty picture of the water in that lake in the mountains. But those are more complicated. They're surface waves, and the restoring force allows for those to be transverse along the surface. All right, let's move on and talk a bit about energy being transported. I think it's pretty obvious, maybe, you know, from experiencing waves like this, that we really are going to be able to transfer energy, right? When you listen to a sound, energy has been transmitted through the medium of air. It's reached your ear, and so there's energy being transmitted. Now, let's say that we've got a wave propagating this direction. Now, I always worry that when they always draw these as transverse waves, but a better representation, if we're thinking of air, would be a longitudinal effect, a compression wave. In either case, we can say that the energy stored in the wave is given by 1/2 k a squared where A is the amplitude. How much does the individual portion of the medium oscillate back and forth? So we could get the calculation from 1/2 Ka squared. That's what we saw back in chapter 14. The problem is, what's little k, right? There's got to be some kind of a stiffness property of the material. So this formula doesn't really work well. There's no value we can put in. What they're telling us here, and they're just writing the formula down, they're not deriving it. We'll come back and we'll write down some plausibility ideas about why the formula has this view to it. So we're going to come back. But I do want to point out and say the energy of a disturbance that's propagating is proportional to the amplitude squared. So how much back and forth does the medium oscillate as it goes by? And then it's also proportional to the frequency. We find out if the frequency is higher, that suggests more energy is being propagated by those higher frequencies. Now, it's also going to have to do with how much mass the medium has. So if I've got if I've got this long piece of steel or something, and we've got a disturbance propagating through that steel, to get the total energy in the entire sample, we just have to put the total mass in. You know, if a wave is propagating through this medium, the mass that we use to calculate the energy corresponds to the mass of whatever portion of the medium we are considering. Now, what usually happens is we divide the medium up into individual slices. So let's look at just one slice at a time, and then we can say, well, the energy in each individual slice is related to the amount of mass in each individual slice. Okay, so that's kind of where we're headed with looking at the energy. Now, a couple things to be aware of here. When we do these slices, what we want to be able to do is think of the cross-sectional area, right? I've got this disturbance. The disturbance is spread out. So the disturbance is spreading through maybe all regions of this medium. I need to know what the cross-sectional area is that I'm dealing with. Now, since capital A is already being used for amplitude, the textbooks does a fallback and uses S to represent surface area. So be prepared, these capital S's in the formulas have to do with cross-sectional area. And they're calling it surface area to justify using S. In any case, we're going to introduce this quantity called intensity. So how intense is the propagation of energy? How intense is the wave propagation? And that is going to be power per area. So that's, power is in watts, so we'll be able to calculate how many watts of energy, how many watts of power are there. And as you know, a watt is a joule per second. So how many joules per second per square meter are being transmitted? And that's what intensity is. So intensity is going to be a very important quantity to us. We're going to put it right up there with energy and power. Okay, so they're kind of introducing with this picture what we're going to mean by intensity. So let's take a look and see. Now, the energy that we have as the wave propagates, this is energy of the medium. So this is the energy of the medium oscillating back and forth. So it's oscillatory energy. It's the same stuff we looked at in chapter 14. Now, what's different in chapter 15 is instead of the oscillation energy staying in just one object, the energy propagates through the medium. So the energy gets handed to the next part of the medium, to the next part of the medium. So as the wave is propagating, energy is being carried from one part of the medium to the next. The energy is being communicated through the medium. So let's look at a longitudinal wave. And so in a longitudinal wave, let's say we have a bunch of different parts of the medium. Again, maybe it's a string like something we have over here. In fact, let's do that. let's start with a one-dimensional example. Let's say that we have a piano string, for example. Maybe it's a steel wire. And individual, actually that's not as good. Let's use, yeah, let's go ahead and just say we have a steel wire of some sort, and that we've got disturbances set up so that they're longitudinal. So individual pieces in this case, kind of like a slinky example, the individual pieces here are oscillating back and forth. Now, it doesn't have to be longitudinal. It could be the individual pieces of the medium are oscillating back and forth transversely. So these could be transverse disturbances, or they could be longitudinal, either one. But let's say that they're transmitting through a fairly narrow material. And so we can think of this energy as being confined to this region as it propagates through. Let's put together some formulas describing how an individual piece, each individual part of the medium, oscillates back and forth. So each individual piece of the medium, here is its displacement as a function of time, is given by an amplitude. Let's use a sine omega t. Turns out using a sine is convenient, so we'll go ahead. We've used cosines or sines back in chapter 14, and using a sine works as well as a cosine. So we'll use this for the displacement of an individual piece of the medium as a function of time, and we'll use this for the velocity. Now, x max, the maximum displacement, would be the amplitude, and the v max is omega times a. Again, formulas from chapter 14. Now, the energy for an individual part of the medium would be given by 1/2 Ka squared. Now, again, when we're doing wave propagation, the definition of little k is a little vague as to how we should represent that. So instead of thinking in terms of amplitude energy, potential energy of the amplitude, let's think in terms of kinetic energy. It actually turns out that with waves, it's easier to do energy calculations working in terms of how fast are individual pieces of the medium oscillating back and forth. So that would be 1/2 m v max squared. That would be 1/2 m omega squared amplitude squared. And that's going to be, we're going to be able to visualize what's going on with that. So what that says is if I take any region of that string, maybe I take the whole length of the wire, maybe I take a small region, any region I look at, the energy stored in that region at a given instant is 1/2 times the mass times the frequency squared times the amplitude squared. So it depends on amplitude squared, it depends on frequency squared. Now, what we're going to do, what you guys can see happening here is, we're going to set this up as an infinitesimal. So what we'll say is that I'm going to take this wire, break it up into a bunch of little pieces, and what we'll say then is each little piece of the wire has a mass, dm. And that means that each little piece of dm has a frequency of oscillation, it has an amplitude. We can calculate a little infinitesimal amount of energy, dE, and then we can divide this equation by dx. So dE dx, that would be the energy per length. So the energy per length in that wire, as a disturbance, as a wave propagates along, is going to be given by 1/2 dm dx omega squared a squared. Well, dE dx then, the rate at, not the rate, but rather the energy per length, is equal to 1/2 mu omega squared a squared, where mu was our linear mass density that we had talked about. All right, so that's looking useful. Now dE dx, that says that there's a certain amount of energy stored right here. The question then becomes, at what rate is the energy stored here cross this boundary that I set up? See, we're standing right there, watching the energy go by, and we've drawn a line on the wire, and said that we are going to count all the energy as it goes by. Right now there's a little bit of energy stored in that region of dx, and it's that much energy right there. At what rate is the dx energy going to cross over to the other side? And that depends on the wave speed. So dx is going to equal the wave speed times dt. The power, the rate at which energy crosses that boundary, is dE dt. I can rewrite this by putting a dx underneath, dx in the numerator and the denominator. And this dE dx, that's the energy per length, which we calculated. Dx dt is the wave speed. So during a time interval, dt, the energy shifts by a distance, dx. That's the wave speed. So this is the wave speed. The power then comes from taking that energy per length and multiplying by the wave speed, and there's our formula. Now, I like keeping the formulas in terms of omega. Omega are more direct. When we're doing these derivations, it's omega that we're working in terms of. The textbook likes to write this in terms of frequency. When you do, and that's fine, when you do that, when you write it in terms of frequency, you get these extra factors of 2 pi out front. So, you know, everybody has their preference here, I guess. But I prefer writing it as 1/2 mass per length, omega squared, a squared, amplitude squared. This is all about the medium. So all the stuff here is the mass per length of the medium, the frequency at which the medium is oscillating, the amplitude of those oscillations, and then you just multiply, at the end you multiply it by the wave speed. And that will tell us the rate. Now, this formula, if we go back, is not the one that they derived here. The one they derived here was for a 3-dimensional medium. And what we've done is we've been looking at just a 1-dimensional medium. So how do we extend it? How do we take the formula, everything that we've derived here, for 1 dimension, along a string, along a wire, how do we turn that into 3 dimensions? And here is the very same derivation set up. Now what we have is we have an extended medium. It's not concentrated or limited to just a wire. So I've got this wave speed happening all over the place. Here is a cross-sectional area. And for this, we use intensity. Intensity is power per area. And so I can write this as dE dt 1/s. This is the power, is the dE dt, same as what we did before. Now we can say that instead of a dx, instead of a little length of the medium where the energy is, now I've got a volume. There is a volume within which oscillations are taking place. That's where the energy is located. That dV is going to be the cross-sectional area times dx. So, ooh, did I write dx? This has a thickness of dx. So this whole volume is dV, cross-sectional area is s. This is dx. So I can substitute those in. What I can do is say that the intensity is equal to dE over dV. Now I put a dV here. So I put a dV on top and a dV below. And the s's canceled out. And for intensity, what I want is energy per volume times the speed of the wave. So instead of the energy per length, it's energy per volume if I'm working 3-dimensionally. So the energy per volume is going to be 1/2 density, not mu, but rho. So that's mass per volume, omega squared a squared. So it looks the very same. The intensity formula for a wave propagating through a 3-dimensional region is going to be 1/2 rho, omega squared a squared via the wave. So the units, just a reminder on units here, so the intensity is energy per time per square meter. And that can also be written in watts per square meter. So that provides us an intensity of the sound propagating through a three-dimensional region, energy of the wave. Let me check the time very quickly here. I think we're coming up on break. Yeah, we are. Let's take this let's look at another item, and then we'll go ahead and take a break. Now, when we're transporting energy through these disturbances, through these waves, often what we'll end up with is a central source that propagates the energy outward from the central source. Up until now, we've been treating these waves as if they're all traveling together. These are referred to as plane waves, and so what they do is you can think of it as, again, a slice of something, another slice, and then the wave is propagating perpendicularly to those slices. That's kind of a beam approach. Now, in this case, we still have those slices, but the slices are spherical slices surrounding the source. In this case, the disturbance is propagating in all regions away from the source. Now, in many cases, it's not that idealized. If I've got some speakers out and I'm listening to some music, the speakers aren't necessarily sending the sound in every direction equally. But what we do is we often roughly idealize this as a central source with the energy being radiated uniformly in all directions spherically. Now that says that the intensity will drop off like 1 over r squared, because that's the rate at which the surface area is increasing. So here's an example. They're looking at earthquake intensity. They're saying that there is, okay, I always get these backwards. I think the P waves are longitudinal and the S waves are transverse. I might have that backwards. You may have to check me on that. But let's say that we have an earthquake and there's a P wave and it's traveling through, I think it's longitudinal, and it's going to be detected 100 kilometers from the source. So we've got all these earthquake detector stations set up, and one of them picks up an earthquake, and from multiple locations we're able to determine that the central source of that earthquake was 100 kilometers away from that station. And that with the earthquake, the energy will be spread out, we're going to assume uniformly, in all directions. So what would be the intensity then if we, for a detector 400 kilometers away? Well, here's kind of what our picture looks like. Here is the source. It's generating energy at some rate. That would be a power. So here is the first station at point A. Here's the second station at point B. For that first station at point A, it's 100,000 meters from the source, and the intensity was measured to be 1.6 million watts per square meter. Now, here are the formulas that we can work from at the two different locations. The intensity at point A will be the power divided by 4 pi r squared. Well, at point B, it's the very same formula. So whatever location is measuring this, the power that we start with, it's the same in every case. The intensity drops off, not because the power is different, but because the distance is different. So as we get farther and farther away, that power, the intensity, will drop off as 1 over r squared. So we can use these formulas. Let's say the power then can be determined, how powerful was this earthquake, by taking the intensity measurement at some location and multiplying by 4 pi r squared. So that would give us a power of 1.26 10 to the 17th watts. That's a lot of watts of power. Now the intensity measured at point B, we can determine by using that very same power, but this time we'll divide through by the larger surface area, the 4 pi r squared. The distance here is 400,000 meters, and the intensity has dropped off by, what was the intensity before? The intensity was 1 million. This is at 62. This should be, it's 4 times as far away. This should be 1/16. So since station B is 4 times, I didn't scale it. Station B is 4 times as far away. The surface area will be 16 times larger. The intensity should have dropped. Now again, this is not including any damping effect. Some of the energy from the earthquake will just go thermal. It's that damping effect that we looked at back in chapter 14. But we're assuming no damping and that all the energy continues to propagate spherically away from the source. So, good example here. This looks like a good place, I think. Let's go ahead and stop and take a break for the break time. And if you guys have questions, let me know.